This is a pre-built version of the application. So if we go ahead and run the server and two clients, so this will be the server, and this is the first client, and this one the second client. So here we will have Alice, and she will pick those two prime numbers, and this public exponent. And Bob will pick those two prime numbers and this public exponent. And Alice is sending this message to Bob, so she would start by mapping the characters to ASCII and obtaining this ASCII message, and then she would encrypt it with Bob's public key, so she would obtain this ciphertext, which she would send to Bob. And Bob in turn would receive the ciphertext and decrypt it with his private key and obtain this ASCII message, which he would map to character and obtain the original message coming in from Alice. And Bob in turn will send this message to Alice, so he would start by mapping the character to ASCII and obtaining this ASCII message, and then he would encrypt it with Alice's public key and obtain this ciphertext, which he would send to Alice, and Alice in turn would receive it and decrypt it with her private key and obtain this ASCII message, which she would map to character and obtain the original message that is coming from Bob. And passive Eve here can see all the communications, so she can see Alice's public key and Bob's public key and the ciphertext messages sent from Alice and from Bob, but in order to decrypt those, she needs Alice's private key and Bob's private key, and she can only obtain those by factoring the n into p and q. So Alice's n into the original p and q, and Bob's n into the original p and q. Now before proceeding with the code, let's do a quick introduction. So this is the extended Euclidean algorithm, and it is used to compute the inverse modulo of an integer. So for example, to compute the inverse of R1 mod R0, where R1 is smaller than R0, that inverse only exists if the greatest common divisor of R0 R1 is equal to 1. So we apply this extended Euclidean algorithm and obtain SR0 plus TR1 is equal to 1, which is equal to the GCD of R0 R1. and we end up with the inverse of R1 in mode R0 is equal to T. And this is an example of computing the inverse of 7 in mode 19. So we end up with 11. Now the Euler phi function denotes the number of integers in Zm that are relatively prime to m, where Zm is the set of integers from 0 to m minus 1. And two numbers are relatively prime if their GCD is equal to 1. For example, if m is 15, then Z of 15 is 0 to 14. And if we want to calculate phi of 15, then we take the GCDs of all those numbers and we count the GCDs with the result equaling to 1. So we have 8 of them. So 5 of 15 is equal to 8. Now if m is a very large number, it is not computationally feasible to take the GCDs of all the numbers from 0 to m minus 1. So we use those two formulas for m and for phi of m. So m is equal p1 to the power of e1 times p2 to the power of e2, etc. until pn to the power of en. And phi of m is equal to this formula. And an example is if m is equal to 200, then it is equal to 5 to the power of 2 times 2 to the power of 3. So p1 is 5 and p2 is 2 and e1 is 2 and e2 is 3. And we apply this formula here and end up with 5 to the power of 2 minus 5 to the power of 1 times 2 to the power of 3 minus 2 to the power of 2. And we end up with 20 times 4 is equal to 80. Now if p is prime, then phi of p is equal p to the power of 1 minus p to the power of 0. So is equal to p minus 1. And the GCD of p and q is equal to 1 means that phi of p times q is equal to phi of p times phi of q. And if p and q are primes and n is equal to p times q, then applying this formula, we end up with phi of n is equal to p minus 1 times q minus 1. So if m is equal to 15, it is equal to 3 times 5, so we end up with 3 minus 1 times 5 minus 1, which is equal to 8, which is the same result that we obtained by counting GCDs. So our goal is to build a prime factorization based crypto system. So we start by multiplying two very large prime numbers, p and q, and obtain the result n. Now it is not computationally feasible to figure out p and q from n. So in our crypto system, n has to be known and p and q unknowns. And we want to set up the system in such a way that there exists a private key d that is the inverse of the public key e, or the public exponent e. But where it is very hard to figure out d from e in mode something. Now if that something is known, then we can use the extended Euclidean algorithm in figuring out the inverse. So the something has to be the unknown in our crypto system, meaning that something has to be based on p and q from here. But we also know that for two prime numbers, p and q, the Euler phi function, phi of n, is equal to p minus 1 times q minus 1. And we know that for very large numbers, it is not computationally feasible to obtain all GCDs and count the relatively prime numbers. So the idea is to use the phi of n as that something and set up the system such that D is the inverse of E in mod phi of n, and E is in the set of 1 to phi of n minus 1. So we end up with those 5 steps. We start by choosing large prime numbers p and q such that p is different than q, and then we calculate n is equal p times q, and third we calculate phi of n is equal to p minus 1 times q minus 1, and fourth we choose a public exponent e in 1 to phi of n minus 1 such that the GCD of e and phi of n minus 1 is equal to 1. And finally we compute the private key d such that d times e is congruent to 1 in mod phi of n. So our public key will be made up of n and e, and our private key will be d. Now to encrypt a message m that is in Zn from 0 to n minus 1, we use the public key n and e to encrypt m and obtain the ciphertext c is equal to m to the power of e in mod n. And to decrypt a ciphertext c in Zn from the set 0 to n minus 1, we use the private key d and obtain m is equal to c to the power of d in mod n. I will start by creating a new project. And to do JSON, I used this jar on the previous project, so let's copy it and paste it here. And we go to properties and Java build path, and the code will be in 2 packages, one for the server and another one for the client. And on the server side we will have 2 classes, a server class with a main method and a server thread class, and on the client side we will have 3 classes, a client class with a main method and a client thread class, and the RSA implementation code will be in this class, and both client thread and server thread classes will extend from thread, and the server thread class will have 3 instance variables, a server and a buffered reader and a print writer. and we will initialize those in the constructor. And on the server, it will accept connections on this port, and we have a set of server threads for the clients that this server is interacting with. And this is just a get method for the server threads. And this method will forward the messages from one client to the other. So it calls forward the message on the server thread, which we will add. And here we are starting a new server thread and adding it to the set of server threads, and then calling the start method on that server thread. And when we do that, and when the operating system decides to, this start will end up triggering a call to the run method. On the server thread. So here we are checking if one client is sending his public key to the other client, then we indicate what that public key is and forward the message to the other client. But in order to decrypt any messages, we need to figure out the private key for this public key. And to do that, we need to do prime factorization of n into p and q. So this should do it on the server side. And next we will do the client side. So the client will keep track of this client username and the n for this client, so p times q, and the n for the other client, and the phi for this client, and the encryption or public exponent for this and for the other client, and the private key for this client. And we will have get and set methods for those. Now going here, we will have those two methods for calculating d, the private key, and returning it, and for calculating phi given p and q, two prime numbers, and for generating the keys So we are making use of those two methods for checking if a number is prime, or if two numbers are relatively prime. So here we are handling P and Q entry and calculating and setting N and phi, and prompting the user for the public exponent E, and here we are calculating and setting the private key, and here we are sending a JSON message indicating what the public key of this client is to the other client. And those two methods, encrypt and decrypt messages, and those two methods do character to ASCII and ASCII to character. And finally those three methods this one does sending messages, and this one handles receiving the public key of the other client, and this one handles receiving message from the other client. So this should do it for this class. And the client thread will have those two instance variables, and will initialize them in the constructor, and the client here will be interacting with the server on this port, and it will instantiate a new client thread and call the start method on it, which will trigger a call to this run method when the operating system decides to do so. So here we are handling receiving a public key, and here we are handling receiving a message. And this handles sending messages. and this method handles the key generation. So this should do it for this class. And finally, let's go ahead and test run the application. So this will be the server, and this is the first client, and this is the second one. And Alice will pick those two prime numbers and this public exponent. So she calculates n and phi of n and her public key and private key. And Bob picks those two prime numbers and this public exponent. So he calculates n and phi of n and his public key and private one. So Alice sent this message to Bob. So she starts by mapping the characters to ASCII, and then she encrypts it with Bob's public key and obtains this ciphertext and send it. And Bob receives it and decrypts it with his private key and maps the ASCII to character and obtains the original message coming in from Alice. And he in turn sends this message to Alice. So he maps the character to ASCII and obtains this ASCII message and encrypts it with Alice's public key and obtains this ciphertext and sends it. And Alice receives the ciphertext and decrypts it with her private key and obtains the ASCII message and maps the ASCII to character and obtains the original message coming in from Bob. Now passive Eve can see all the communications. So she now knows Alice's public key and Bob's public key, and she can see the ciphertext communications between Alice and Bob, but in order to decrypt them she needs the private key for Alice and for Bob. And to obtain those private keys she needs to do a prime factorization of n into p and q of both public keys. So we need this p and q and this p and q.